the WebEx is stop sharing.
It stops sharing, or really? Okay. Sometimes WebEx is little odd. Okay, I see. Interesting. Let me try it again. Because when it was in the view mode. Okay, now let's try this.
Oh, it's stop sharing again.
I think what is happening, let me duplicate slideshow. If I do duplicate slideshow, I did a duplicate slideshow. Maybe that's what is causing it. Otherwise, okay, share. Let's see. Share. Let me share the window. Let's try that. How about now? Is it? See, the problem is it's fine now. If I do view, it might stop share again. Hold on. Is it still there?
Can you go to the last page?
Actually, but I have to also. How about now? But I have to display the setting also because my setting is swap.
This is what displaying on the.
Oh, really?
On the WebEx.
Okay, that's okay. Now, okay, how about it? Didn't change?
Yeah.
Didn't change, huh? Okay, if I do the display setting, let's swap duplicate slide. So I wanted to duplicate slide. So let me. Okay, now it is changing, right?
Yeah.
I think a little, yeah.
It's a little bit slow.
That's okay. I think that always like that, right? Yeah.
Two, three papers.
Yeah, I think it's taking time. Oh, yeah, it's taking time. That's all. Yeah, I think let's see. It's not done yet. Press.
Oh, I thought maybe not in the first one. Yeah, so it's not in the full screen and it changed. I can tell. Yeah.
So should I not do full screen then?
Maybe. So I think this one is blue.
Oh yeah, sure. Yeah, let me just disconnect my VP. Share it. I think we'll window share. Okay. Let me go to back. Yeah.
Yes.
Okay. I think I can just do that then. Is that okay?
Yep, good.
So I should not do full screen then? I should just do this.
I think it's okay.
I think as long as people on the WebEx can see it, right?
Yeah, so on the web it's okay at this moment.
Okay. I mean, there is one animation I had. We'll do that later, but yeah, there is one thing I have an animation here. So in this case, let me see. So you were there, right?
Yes.
Let me, if I do animation, just see whether you can see it. Oh, doesn't break. Okay, so if I Do you see anything happening? No. Oh, no, no, no. 1 second. Let me just click. Oops. No. Do you see anything? This guy moving around? No.
No.
All right.
Maybe try using their software instead of doing on the web.
Instead of doing the WebEx, I mean,
Yeah. Okay.
okay, let me try that. So I'll get out. Should I leave and try again? Let me try again. Okay, now let me share. Yeah. Okay. Hold on. How is that? Do you see anything? It should be, right? Okay. So now I just have to make sure duplicate thing. Slow. Okay, good.
Not in the full page.
No, it should be right. I just did that.
Oh. Yeah. In full page.
Okay, let's see if this guy moves.
Yeah. I saw it.
Oh, okay. All right. I think let's see if this guy moves. Oh no. Wait. Excuse me. And we should. Okay, let's see first. This changing or not? Is changing? Why it's not changing? Okay, it changed. It's a little taking time. That's okay. Okay, so I have a lot of materials. Let me know how much time I have. Accordingly, I will adjust. Okay, so I think I met everybody. I'm Ashutosh. Nice meeting you. Yeah. All right. So I guess well, let me know when we should start.
We can start.
We can start now.
Yes.
So we have some green service. I think I got introduced on what do you do in the school. Let's see.
So I'm a teaching professor
Okay.
here at in the computers,
Let's see.
and I teach operating systems, and I'm still getting my PhD. So
Oh, okay, that's cool. I also did my PhD part time, and I was working at Columbia Computer Science Department, Columbia University. Then I moved to industry, and then I was in the industry for a long time. And recently, last 8 years back, I moved to Johns Hopkins. Well, I'm in the applied physics lab, but I have some dual appointment with Whiting School of Engineering. So that's how I am. So I think I got. And your area? What is your area?
mechanical engineering.
And which the topic?
My research topic is on batteries.
Batteries.
Yeah.
I did some work on that. We'll talk. How about you?
Impulse mechanical. Mine's more heat transfer.
Okay. Mechanical is, yeah. So are you looking into battery, how to increase the battery lifetime?
So instead of using lithium batteries, we're designing zinc batteries because they're a lot safer and less flammable.
Okay.
So we're trying to make zinc batteries have high energy density like lithium batteries.
I did some work on how to increase the battery life for the satellites long back. Like looked at the depth of discharge. Then I tried to see how the traffic, broadband traffic can affect the battery life because they're putting the satellite.
Mhm.
So because you have to increase the lifetime of the battery, right? So that's how it was my research. And then I changed my topic. That was I was trying to do some research there, but then I changed my topic. It's very multidisciplinary. So yeah.
The semantic.
Mhm. I know little about it. I mean, I know 6G is looking into that. I am not an expert in that, but I know my colleagues, they're doing semantic. My focus is, well, actually 6G looking into that. There has been a lot of research in semantic. I mean, up and down, just like AI/ML, right? AI/ML is picking up now. I mean, AI/ML has been there for a long time, right? I mean, I'm talking about like early 2000, late 90s. And now coming back again with the new applications. All right, so should I start, Venki?
Yes.
All right. So how much time? About an hour?
Yeah.
About an hour should be
I
okay.
think it's good for 1:30.
Okay. So if you get bored, let me know. I can stop you. You can talk something else. I'll keep it very informal, right? Because sometimes you have too much of information overload is not good. So I choose a topic. I think initially I had something about mobility modeling, but I thought this will be more interesting and more timely because what's happening in the next generation wireless security and how the AI ML. So I'm trying to fuse it together. So I'm with Johns Hopkins Applied Physics Lab. We have a Doctor of Engineering program at Hopkins. I'm the director of that. That's kind of my part-time appointment. I teach classes at Hopkins and also we have a engineering for professional program. So you probably know about that. I don't know, UMBC, do we have like people who are working in the industry, they have master's program? Right. And I know some of my colleagues, they're doing part-time PhD here. They work at APL. And I was telling Professor Anupam Joshi, he had given talks at some point later in the past. And I'm also involved with a lot of this IEEE and ACM stuff. So that was kind of, but I worked at AT&T, Belcore. I worked for a startup, security startup. And then I started my career at Columbia University. Like I was a staff lecturer in computer science, the computer science Columbia University. I'm taking care of their IT and I was finishing my PhD. So it's, okay. So now my talk, this is my because I know there are some students that are faculty, and some of you may or may not have real wireless backgrounds, and try to balance my talk a little bit to give you a little bit high level. I'm not going to talk about any equations in this my talk. Little bit of what is going on in 5G 6G area. Hello, how are you? So what's happening in, we are all using 5G and 6G. I do a lot of work on development of 6G as well. So I'll talk about that. Then I'll focus a little bit on the security side. What are the potential threats we have if you're using 5G, right? So when I was in AT&T, I was with the Chief Security Office. So we had to deal with a lot of network end-to-end security, like device security, application security, network security, all those, right? Because you have to make sure your users are protected. I'll give some experimental results also. We at APL, we do a lot of work with Department of Defense, Department of Homeland Security, and these are unclassified stuff. I strongly believe if you have some idea, I do a proof of concept and see how it can be used, right? Eventually it has to be transitioned. And there are some security use cases. Then I see with the advent of AI ML, we are all started seeing how AI ML can benefit. But at the same time, AI ML has its own problems, right? So I'll talk about that a little bit. Then if time permits, these are some of the things I have been very much involved. So IEEE Future Networks, I'm one of the founding co-chair. We started that in 2017. And the idea was to see 5-year, 10-year, 15-year, 20-year, how the network is evolving. We don't want to call it 5G, 6G, or 7G. And this is open to anybody, like students. You don't have to be a member also of IEEE. Then there are certain things I did on digital divide, like there are many people in the world, they don't have connectivity, underconnected. So we also started that. Have you heard about Vint Cerf? Probably know Vint Cerf, Dr. Vint Cerf, who is the father of the internet. Vint Cerf, Bob Kahn, right? These are the two guys with Len Kleinrock. So if some of you are in the information communication system, they in 1969, they actually started the ARPANET, right? Which became the foundation of internet. The fast packet switching, what we are seeing today, they sent the fast packet in 1969 from SRI to, UCLA to SRI. And talking about ACM, Len Kleinrock, he gave our inaugural talk for the ACM Baltimore chapter back in 2022. He gave a remote talk. It's amazing too. He's like 91-year-old. You know, these are the people who really build the whole foundation of the internet, which we are enjoying today. And that is in IEEE, we have created an innovation testbed. So we realize that many places in the world, they don't have access to the real experimental testbed. So at Hopkins, I teach 5G, and my students say, well, Professor, you're teaching this 5G, all these protocols, this and that. Then how do I get access to it, right? So we thought, you get, as a faculty, they get grants and they can create testbeds, but there are many universities around the world, they don't have access, right? So we wanted to see how the students can get access to it, right? So we just built a testbed. I'll say a little bit about that. So that's kind of my thing, and we'll see how time goes. Then if you get bored, let me know. I can change topics. We can talk other things. So I just want to set the stage here. If you look at, and some of the pictures I've taken from Leon Garcia's book. Leon Garcia is a professor in University of Toronto. I teach a data communication course. And if you see, before we get into 5G, how things have evolved, it's good to know some fundamentals of what's going on. You will be recording. You're recording it?
Yes.
Okay, good. So if you look at the real old days, right? The horse, pigeons, Pony Express, and then Morse code started with optical telegraph, electric telegraph, right? These are different timeline. And Graham Bell, you see that 1875, that sketch of how telephone started. So I used to work for AT&T Labs. So you have a picture of, if you ever go to Bell Labs, you'll see the picture of Graham Bell and the actual telephone, right? I probably don't have it in the slide deck, but you can see the real telephone that was kind of used. So that 1875, then 1878, right after that, we started the circuit switching. And if you see, I think many of you probably I don't know, some of you, I still remember when I was growing up in India, I had to make a trunk call from my home state to another state. So I had to call the operator. Operator says, well, your turn will come 30 minutes from now because you don't have enough switches. So, and then he said, okay, now I'm connecting you to this person, right? Then he does this connection. This is how it used to be, right? All manual thing. And then PSTN started after that with circuit switch, like digital stagger switch, digital switch, all those things started. But at the same time, as I was telling, the packet switching, which you all use today. So they're basically message switching, circuit switching, packet switching, right? So message switching was optical telegraph or electric telegraph. Then circuit switching is which we have been using, people still use in many parts of the world, where you have this RJ11 connection and people just connect, right? I don't see even my mom in India, we don't have any PSTN or circuit switch. Even nowadays, I don't know how many apartments they still have that RJ11 connection. When I came as a student in 1987, we used to, I call the, whatever, the Verizon Bell Atlantic, I don't know, whatever, 9X maybe. Okay, they come and activate that port, right? And nowadays, everybody using IP based phone, right? I mean, PSTN had its own advantage. You get a power and everything out of this thing. So packet switching started in 1969 with the fast packet. Then TCP/IP protocol, which we use, that was invented, right, by Bob Kahn and Vint Cerf. And then other protocols like streaming and etc. started. And Ethernet, we all use RJ45. That became a standard. 802.11, which is Wi-Fi. And now we're in next generation Internet 2020. Things have been evolving. So I'll give you some little background of cellular before I get into 5G, what 5G is. So this is how the evolution is happening. And so why, I know there are a lot of students here, so please allow me to say what is the objective of a research, right? So there has to be some end goal. Who is going to use it? I mean, we can always do interesting research, but at the end, who is going to use it? I mean, for example, you're talking about battery, right? So you must have sorry, what's your name?
Anessa.
Anessa, right? Anessa?
Yes.
Anessa. So Anessa, you're doing battery research, so you have to know who's going to use it at the end, right? I know you have a nice algorithm. It has to have a use case, right? So this is where what we think, again, this is my advisor, Professor Henning Schulzer from Columbia. He says, communication is the civil engineering for 21st century. So in 20th century, civil engineering was marble, right? We were building like towers, skyscrapers and all those. And 21st century communication is the civil engineering because it can give us a lot of things, right? So what I'm showing here is an example of a smart city. So if you see, there are different types of end users. You have robotics at home, connected house, security surveillance, intelligent transportation system like car-to-car communication, water quality, smart wearables. So if you have to support these, they have to be interconnected, and each of these has different KPI, the key performance indicators. Some need high bandwidth, some need low latency. So we need some kind of a substrate or foundation that can support this kind of communication, right? Like flexibility, scalability, and all those. So this is where we begin to think, do I need a new communication infrastructure? Do I need a new protocol to take care of the application need, right? So that is the motivation. So I was trying to create the motivation why we need. So what you're seeing here is, given that, and I'm going to focus only on this wireless side here. Let me stand up so that I can be a little bit more effective. So what you see here is in 1980, this has been evolution, right? So we are somewhere here now, right? At 5G. It started in 1980 with 1G, which is analog communication. Every 10 years since then, there has been a new cellular generation, right? And I had been involved personally with 3GPP2, 3GPP in some of the standards. But if you look closely, you see the amount of bit rate. So this was analog, this is digital. So p kilobit per second, 100 kilobit per second, the things are moving. And there was two institutions, 3GPP2, which is third generation partnership program. This is the standard. So these are the standard bodies who define all the 5G, 6G stuff. There are other standard bodies like ITF that define protocols like DSCP, DNS, etc. And at the same time, the IEEE also doing its own job. I'll talk about that. And there are 802.20. So this is how the things are evolving. And 2008, 3GPP2 got, basically said, okay, we don't want to have two parallel organizations. They all jumped into 3GPP. So you see different types of access, code division, multiple access, time division, multiple access, frequency division, multiple access, etc. Right? And now in 2010, 4G was deployed. You see these uplink, downlink. These are the 80 megabit per second, 360 downlink. So the speed has been increasing, right? So most of until 4G, it was just the speed. But when the people in 2015, people started. So 2010, 4G was deployed, which is called long-term evolution. Then I have to tell you a little bit how it works. So that is an organization called ITU, International Telecommunication Union. So that consists of people from around the world. So every country has a representative. So what they do, they come up with a set of requirement. They call it IMT. So before 4G was deployed, that was in 2010. So in 2005, they hand out a requirement document saying, hey, this is going to be the application, these are the requirements, there's a bandwidth, all those things to 3GPP. So 3GPP takes 5 years before they deploy it, right? Standardize it, then it start getting deployed. Similarly, same thing happened in 2015. They gave something called IMT 2020 to 3GPP, and they started standardizing. 2020, they started deploying. So this is where we are right now, right? So if you see the 5G is not only the bandwidth, it has other characteristics. So as I was showing previous chart, there are some applications that need low latency, right? There are some applications which are like sensors. So they had to define new infrastructure, network architecture to support this kind of applications, right? So this is what 5G has been. So 5G is being deployed, not everywhere, and there are different versions of 5G I'll talk about. And then we are in 2026 now, right? So 2025, so I was in South Korea, we had a kickoff for 6G. So what is 6G? How it is different than 5G, right? Because you have to think about new requirements again. So the IMT gave a similar document to 3GPP. So now you have to start working on 6G, right? So I'm also involved there. So if you see here, there are enhanced mobile broadband, massive machine to machine, and low latency application. Here you have additional things. You have ubiquitous connectivity, integrated sensing application, high reliable, low latency application, immersive communication. It's not very visible, but I'm just reading it out. So they had some additional requirements, right? So I'm just setting the stage why we need all this. So now you know a little bit about this, but at the same time, this is a chart from one of my colleague, Gerhard Petweiss, with his permission, I'm using it because I like this chart. So what is happening now, you see how the evolution happening on the cellular side. At the same time, we all have been using Wi-Fi, right? And we cannot completely trust Wi-Fi because it is there. It's going to be there. And so I remember in Columbia, I was there from 1989 to 97, Columbia University, and we didn't have Wi-Fi then, right? And it started in 1995, it became a standard in 1995. So there is a 802.11 working group within IEEE, just like 802.3, which is Ethernet. It's called LAN MAN Standards Working Group by IEEE Computer Society. So you see there has been an evolution of 802.11 also, and now 802.11be, which is Wi-Fi 7. And I was a little bit involved there in the development. So it is going in parallel, right? So there is a coexistence, the interoperability, you hand over from cellular to Wi-Fi, those things happen. So we should not forget, at least research community, a lot of interesting issues there. So this is Dorothy Starley. She was the chair for IEEE 802.11. She gave a talk at Hopkins once, and she's now the president of IEEE SA. So if you see, I just wanted to compare how things are evolving. So 2011, 802.11b is Wi-Fi 7, right? So if you see the bit rate, 600 megabit, 7 gigabit, 9.6 gigabit, 40 gigabit, right? So this is Wi-Fi is also comparatively, just like cellular is evolving, this is also evolving, right? So there are a lot of application each one has different characteristics. Some application Wi-Fi is better, some applications cellular is better, right? Okay, then let's see why we need 5G, right? So very high level again, I'll talk about more. So first of all, better security, privacy, identity protection, real-time experience, seamless experience, personal experience. On the service side, interaction, charging, quality of service, context, right? I mean, these are the high level thing, and we'll see how they build the requirement and came up with the infrastructure, right? Let's look at that. I'll get into security later because it's good to know what 5G network is first. This is again another motivational slide just to set the stage. So what you see here is, remember I talked about the first slide or second slide. There are different types of applications. They have their different key performance indicators. So there are some thing that can be, and you see the bandwidth requirement and the latency requirement here. There are other things like programmability, augmented reality, and these are different things. So what you see here, there are some applications, they have up to 100 megabit per second. So you really don't need 5G there, right? Because 4G can support that. But there are applications like the virtual reality, let's say, it needs 10 gigabit per second and your latency requirement is 1 millisecond. So for those, you need 5G, right? So what I'm trying to say is there are, depending on the application, it is decide, right? Do I need 4G or 5G? And similarly, when 6G is coming up, there'll be another quadrangle there. They have a high bandwidth, low latency, etc. In addition to that, they have programmability, orchestration, resilience, those things also there. So this kind of sets the stage why we need 6G. Yes.
So is the goal what we're going from 4G to 5G is that we're able to now have more devices to be able to connect to the web?
That is one aspect, right? Yeah, absolutely. So that like the connection density, we are talking about that. At the same time, the bandwidth, right? But there are other aspects also like the programmability. So I'll give you an example. So let's say we are watching soccer game or football game, right? And you see the thousands of people, all in a sudden somebody score a goal. And that's called performance overload. Everybody starts taking picture and uploading it, right? So in the old days, I remember because I used to maintain the network, we didn't have the ability to scale up the network, right? That's called resilience part, right? So if all this bandwidth, let's say get a peak from 10 megabit to some gigabit, right? I should have enough provision to support that, right? Otherwise, there'll be denial of service attack. Nobody can, performance overload. The same thing on the security side. I'm just answering a question is in more than just the bandwidth and connection density. And you'll see that because that's why I call it system control, because programmability. If somebody is attacking my network, right? How quickly I can detect who is attacking and I can stop the attack, right? That's another programmable. I'm just giving two examples so it is bandwidth, connection density is one thing, but there are others too. Okay, so now at a very high level, so enhanced mobile broadband, machine to machine type, ultra reliable, low latency, these are the three high level types of application. And this has been taken from NGMN, which is Next Generation Mobile Network Alliance. So they look at the business case. I don't know if nobody is here in the business, but if there are people in the business, they should work with the technologists hand in hand. Otherwise, we'll just keep on developing the technology and we don't know the business case and the technology will die, right? So any of us, we are doing research. You'll be happy if some of your research gets, deployed. So my research will hand off optimization. And maybe 5G now is going to use that because there'll be a lot of handover. You'll see that. So what is happening here is broadband access everywhere, high mobility, massive Internet of Things, tactile internet, natural disaster. So these are the kind of services, remote surgery, broadcast service. And if you see underneath, this service is not only bandwidth, right? If you're moving at a high speed, how do I maintain the continuity? So these are the things we have to think about. If I'm doing a remote surgery, that means I need low latency, right? The doctor need to, it cannot wait for like few seconds even, right? So that's where, some of the services they fall into enhanced mobile broadband, someone like massive sensor, some are like reliable low latency, right? So that's this is how it is happening. So let me go a little deep here. So when I said KPI, these are the kind of things we are talking about. So you see the broadband access, dense area, these are the different kinds of situation, right? Machine to machine type communication. And then how much of data rate you need. For example, downlink and uplink. So if you use broadband access in dense areas, I need to have downlink is always more than uplink, right? Because we are just downloading. And the end-to-end latency 10 millisecond. Then mobility again on demand, whether you're pedestrian or you're going in a car or train. So what happens, the ITU, they give this kind of requirement, then 3GPP has to define. I mean, maybe 4G didn't have this, we have to add new elements. That's what happens. So just to give you an idea. So for example, here, let's see in the mobility, resilience, traffic search, right? Regular communication, ultra low latency, you have to have less than a millisecond. Yeah, anyway, so this is just the use cases. So this is how you do. Then overall systems performance, right? Systems requirement. So that was the user side, how much I need. But depending on how many people you're serving, it's like Manhattan type, right? Or it is a rural type, you'll have broadband access in a crowd, indoor high, ultra high broadband access. So, and you're talking about the connection density when you're asked that question. Again, you see this kilometer because it is in European standard, they do it that way. And then the traffic density. So this is where you define the overall system parameters, right? So if I'm a network engineer in AT&T or Verizon, I have to see, am I deploying in a rural, semi-rural or semi-urban or real urban, right? Then I can change my network accordingly. Okay, now I want to, before I get into 5G again, 6G has already started. So we should know what 6G is looking into now, right? So this is from the kickoff slide last March, 2025 March. So they said, okay, let's look at why we need 6G. Just like I was saying, why you need a new cellular thing. So support for new services, again, application, right? Like immersive communication, integrated sensing, AI-based revenue growth monetization. You have to have a business case to monetize the network capabilities and support diverse application. This is a big thing now, AI and automation. How do I use AI for network and network for AI? So I have to restructure my network to support AI components, AI agents, but I can also use AI agents to make the network more optimized, right? And I'll talk about the security aspect later. Energy efficiency, sustainability. This is also, they are looking into reducing energy consumption, promoting environmental sustainability, like, the base stations and all those. Spectrum efficiency, dynamic spectrum, because that is the ultimate thing on the radio side. I'll give an example of ubiquitous coverage. So now it is not here just connected to cellular. You move from cellular to Wi-Fi to satellite, right? How do I maintain that? Then, so having worked in an operator like AT&T, I know how important it is for management to reduce the capital expenditure and operational expenditure, because if you want to reduce the cost of the end user, you have to reduce the cost of the capital expenditure and operational expenditure is important, right? Then service reliability, network simplification. So these are the goals. And so now, I mean, this is why you need 5G, I mean 6G. Then, then they started the high level record sustainability, resilience. This is what I was just giving an example. If heavy traffic disasters, how do I still make sure my quality of service is not compromised? Post-quantum security, I mean, these are the things that started looking, customer experience, efficiency, interoperability. Again, just want to see where we are going, where we are, and what are the things. I give you two use cases here. This is what I call interoperability, converged networks, they call it. So yesterday I was giving a talk, an IEEE webinar for rural communication, right? So, I mean, we live in United States, close to Washington, D.C., we have access to 4G, 5G, whatever, right? There are people still don't have access. They still use PSTN. Sometimes, they have just satellite access, no, nothing else, right? And again, not even broadband. We all use Wi-Fi. So in this case, example is if these are the mission critical users, they have to communicate. They have to have some converged network. So these are the gateways. So if I have a PSTN, and this is my 5G core, right? So I have to have some gateways. So the convergence interoperability is important. Okay, that's one example. The second one is, I don't know, this lady moves if I try. So this is what is happening when you're changing this is called ubiquitous connectivity, right? So if you are connected to personal area network, let's say Bluetooth. So this lady is trying to take care of a patient and talking to the public safety command center. And she moves from personal area network to, that is an animation, I'll see if that works. And so in the process, it changes from Bluetooth to Wi-Fi to go to service provider, then come to another provider. So in the process, it still has to maintain the continuity and the quality of service and priority. Okay, I think it's moving, yeah. So this is what is happening. So in the process, she's changing her connection and to different places. She may even go to PSTN, but I want to make sure that continuity is maintained, right? So there is a lot of interesting research there. I personally have done some work before. The another example I'll show you, this is from 802.21. So we all experience that today, right? So if there is a user is connected to cellular, and this user has to pick up his or her friend from the airport, right? So he starts a communication, then goes to a cyber cafe for coffee or something. So disconnects from cellular, still talking to somebody, right? And then get a coffee, then goes to car again, goes to the car, then Wi-Fi link was going down, so connects to a cellular, and then at some point, talking about battery, right? Let's say some of the cellular connection takes more battery, right? I don't know if you have studied that. This is the traffic thing, right? And so battery is going down. Now I have to switch to a different, such a policy-based handoff, right? I switch to from WiMAX or 4G to GSM, which is low bandwidth. So I'm adaptive, right? I'm trying to see which one I should choose. So there's a policy-based handoff, but it's not just signal to noise ratio. And so I switched to a different thing to save the battery, right? And now then I go to the airport, I switch back to the Wi-Fi. So you see it's a very simple example of, so how do I maintain? So this is an interesting research area, right? If I'd have given the other talk, I'd have talked about a lot of mobility models, but that would have been a little boring. So I want to show you what IEEE, this is a work I was involved in 2008 and 9. So the example I gave, you saw the problem, right? How do I maintain the connectivity? So we came up with a new standard called 802.21, media independent handover function. So what you see here is a layering, right? In internet layer. So you have Ethernet, this is Wi-Fi, you have satellite, 4G, 5G, right? If you're handing over between all these networks, how do the upper layers should not know whether I'm changing from Wi-Fi to Ethernet to something. They should be completely opaque, right? They should know that. So we came up with some way of abstraction like media independent handover function. So for example, if I'm about to hand over, I need to know who are my neighboring networks. So if I know ahead of time, I get the information about that. So that's called information service. Then as I'm moving away, I say my link is going down. We prepare for the handover, right? So these are the link events. Then I say, now you hand over, right? And I'll show you some experimental results. So this is what IEEE did. Now 3GPP, oh, this is the result, right? So what I'm showing here, using that framework, how we reduce the handover latency. So in this case, I'm moving from one Wi-Fi network to another Wi-Fi network, right? Because the subnet change, I get about 4-second delay. But we use this framework, if you can see here, we have an information server. So my link is going down. At that point, I get ready to connect. Then I connect. Then I get my traffic. So from 4-second delay, I get no delay and 0 packet loss. Okay. Similarly, for 802.11 to CDMA, I had the same situation from 18-second delay to no delay. So this is an application of a framework that we developed and how we manage. So this is, I'm trying to say theory to practice, important to connect that, right? Most recently, 3GPP that develops these standards, now they have come up with something similar. So they said, you see 5G, either I use 5G or Wi-Fi, I switch from 5G to Wi-Fi, or I can split the net connection, right? Some goes over 5G, some goes over Wi-Fi. So this is also being done, right? I'm just trying to show some of the ubiquitous connectivity aspects. Okay, now let's get into the 5G thing a little bit. So what I'm showing here is that currently everybody has 4G network, right? So this is how it is. So LTE, this is the G node B, E node B, this is your packet code. These are the, so when you see the access tower, you connect to the access tower, then there is a data center in the backend, right? So that's how you connect. So now this cannot happen overnight, right? The standards take 10 years. So if somebody wants to transition to 5G, unless you're a completely legacy operator, I mean, greenfield operator, you start like, I think, did you grow up in India? Where did you grow up? No? How about you? A little bit. Anyway, so I just give an example of, there's a company called Geo, and they didn't have any 3G. They directly went into 4G, right? So there are advantages now using this, but AT&T, Verizon, they have to move here, right? But things are not standardized right away. So what they do, they call it option 3, which is the non-standalone. So in this case, they still use this code. This is the access, but new radio is 5G, right? So it's like a hybrid. So there's a transition thing happening. So many of the, even now, AT&T, I don't think is completely 5G, except for T-Mobile, who is doing this. So we'll focus our study on this, not on this, right? I just wanted to make it clear how the transition is happening. So this is, now comes the real complexity, right? How the network looks like. It looks very complex, right? So let me tell you, so what happens, there's the end user, which we are all using. There is a radio network when you connect to the access tower, right? And once you leave the radio network, these are the cores. So which is core network means the actual machine room. So this is where you see there are a lot of components. And the whole idea is, this is the 5G UE. It has to connect, get authenticated. And you see those N numbers, those are the interfaces, because they have to use certain protocol. So when I turn my cell phone on, it searches for the access tower. It connects to the access tower. Then it goes and talks to a bunch of authentication, authorization components here. I get authorized, right? If I haven't paid my bill, then it's okay, no connection. I cannot even communicate. So once I authenticate, then I have to send my traffic, right? And this is called user plane. So the user plane function, then I can go to internet. I can do voice over IP. I can go to my intranet. So this is how things work. Okay, just to give you an idea. So now when I like to overlay the security later on, I'll tell you what happens. Okay, now we are all engineering folks here, right? So we have to go a little bit deep. So what happened is you saw so many different components, like user endpoint, G node B, access mobility management function. I'm not going to talk about what they do, but each of them, they have some interface because they have to communicate, right? And you need a protocol so that they can communicate. So if you see, majority of the protocols, they're using HTTP now. Used to be diameter type protocol, which is a ITF protocol, but there are other protocols here. So this is how you go deep into a network. If you have to do an analysis, you have to open up the whole network and then see what are the potential risks, right? Okay, just look at that. So now we have to look at the security. You have to see, are there any security issues here? Are there any security issues in protocol, right? Where the attacks are coming? I'll talk about that. Okay, then the other thing I think somebody was asking, I think she left, but she was asking about this connection density, etc. Right? So there is something called spectrum, and they have a frequency, and depending on which frequency you're using, your bandwidth will be different. Supported bandwidth will be different. So if you are using a high frequency like 2430 gigahertz, that called millimeter wave type, then your frequency is high, your bandwidth is high, but your coverage will be low, right? It's like a three layer cake, right? Upper layer, high bandwidth, high frequency, then mid layer, then the bottom layer, right? But T-Mobile, for example, they started deploying the low band. So they said, okay, we have universal connectivity, nationwide connectivity, because they deployed low band. AT&T Verizon started doing high band. They said, okay, I have a high speed, but they don't have coverage everywhere, right? So think about like Manhattan, you have to provide this, you have to do lots of towers, right? So that's called density. You have to have lots of dense access towers. So depending on, again, the country regulation, the needs, is a rural environment, what is the application, you can define, should I use low band, mid band, or high band? So people are mostly settling down in this area, sub 6 gigahertz, right? That's mid band. Okay. Very high level again. I should have had these slides before. So if you look at on the right hand side, that's how it is, right? You have an endpoint, G node B, then S cloud for support low layer latency, then you have this core, then you have the whole data network. So if you see on the radio side, 5G has high bandwidth, new radio, ultra low latency, millimeter wave, like 6 gigahertz to 100 gigahertz. I just showed massive MIMO. So these are on the radio access side. Now, if I go to, and this is some examples of how the design in Nokia, for example. The next one is on the core side. So core side means if you see core, this is the core, right? These are the different components I showed just before. And they have additional, I think she was asking question, is it the connection density or something different? So you have software defined networking. That means something happened in the network, how quickly I can program the routers and firewalls, right? How quickly I can instantiate additional functions. That's what orchestration, mobilized cloud, that gives you low latency application, network slicing. That will give you like quality of service. For example, in this case, if you have an automotive application, medical application, or somebody's streaming traffic, I need high priority for the mission critical users, right? That means I need high CPU, high memory, high core bandwidth. So you have to plan it accordingly. That's called slicing. Then your radio access network is getting also cloudified, everything virtualized. A service-based architecture means service-oriented network. Then a multi-tier networks, the macro cells, small cells, I showed you, right, how you move between different types. They call it headnets, device to device. So these are the very high-level thing. And what you're seeing on the right-hand side, that's just called virtualization. That means in the like 2012 and 13, you need a Cisco router, Juniper router. They're all hardware, their own monolithic proprietary system. Now it is a Linux box, OpenStack, Linux Foundation has done lots of open source, so people are using that. And the VNS of the virtual network function, that means you have the ability to scale up as quickly as possible. Okay, now let's get into security. So I will say what's very high level, what is going on. So now you got an understanding of how network looks like. So this is a very high level classification, and I'll try to see how it could be applicable to 5G, right? So denial of service, blocking completion of mission tasks. So what happens is, I teach a security class, so I'm very high level, I'm telling, if a server gets bombarded with lots of requests, let's say your DNS server, right? That gives you the domain name, or your SIP server, then nobody can access that. That's called denial of service, right? Because the attackers are attacking and the good people cannot connect. Degradation means decreasing the speed, quality, and the other performance. If the doctor is doing some operation remotely and somebody comes and changes the speed, then cannot do the operation properly, right? He cannot see it properly also. Data manipulation means altering the information available to decision makers, right? So that's a bad thing. Data exfiltration, again, the information about the mission details. So I can get into the server or get in somewhere and man in the middle attack. External pivoting means sometimes there are a lot of servers which are heavily protected, but other servers are not. So you connect to the servers those are not heavily protected and then jump in, right? So basically that's what happens. So once you know that, then you have to have a risk. So this is from the NIST. So so risk is a function of likelihood and impact. And likelihood is a function of vulnerability, exposure, threats, mitigating control. So I like to avoid, let's say in UMBC, right? Your IT director or chief security officer like to make sure, everything is secure. That means I have to reduce the risk. So the impact has to be less and likelihood has to be less, right? That means I need to have more security controls. So now, once you determine the kinds of security out there, what kind of control you have, then you can change your risk factor. I'll give you some example. I'll finish by 1:30. I just want to make sure. So now I'm bringing it back again, the actual network, right? So now let's see what are the security problems. So I still my end user, I have a radio access network, I have edge cloud to support ultra reliable low latency, I have a core. As I said, I can move from Wi-Fi to core network, right? And back and forth. Then I go out to the internet. So for example, you're browsing an internet. How does it work? So well, this is a battlefield. Let's try somebody. So you connect access tower. This is the RAN. Then you get authenticated. Then you set up the actual path. Then you go to the internet. When you're calling somebody using, let's say, voice over IP, you go through another cloud called IMS. If I'm roaming somewhere, let's say last 2 weeks back, I was in Japan, and then I connected to the Docomo, and then my home network is AT&T. So I come through that SEP proxy and connect, right? So this is how it happens. Now let's see where the attacks can come. So first is attack can come from the endpoints. We may or may not know. My end device may be malware infected, right? I don't know. So they may sending lots of attacks. I'll show you some experimental results on that. Attacks can happen on the air interface, like jamming, right? We can do a lot of jamming. Somebody can do physical, the remote radio head, which are the access tower. Somebody can go and do, physical access to the G node B or changes the configuration. Now, once I leave the access tower, this is called backhaul or mid-haul, right? And now I have edge cloud. Before even I get to edge cloud, people can do man-in-the-middle attack there, right? Okay, then once I get to the edge cloud, they're all virtualized. So there may be third-party application may do bad things. Attacks from Wi-Fi network. So I may be connected to Wi-Fi. Through Wi-Fi, I can send attacks. And folks in Belgium, they discovered some interesting types of attack. Then over here, insider attack, somebody can get access to the actual database, right? Then they added new things like orchestrator, software-defined network, which is API. I don't know if anybody you must have used API, application programming interface. Then you have attacks from the internet and other networks, right? That can come. So typically people have firewalls, but sometimes the firewalls are not properly configured, right? Then you have problem. Then the attacks from the roaming network, the example I gave, if I'm visiting Japan, and then if it's not properly secure, I can do roaming attacks. So you get a high level view of the threat vectors. So what has happened is, how do we tackle this now, right? So 3GPP is charged of defining this network, but at the same time, they also have the responsibility to make sure the network is secure, right? Otherwise, nothing can work. So they came up with different types of security domain. I'm not going to go deep into that. Just to give you an idea how the security architecture is defined. Every time you have a new network, similarly, Wi-Fi has a security network too, security architecture. So they have access security, domain security, application domain, these are all different types of security. And the way it happens is, this is called, I don't know if anybody knows about this key stop, and some of you probably know that. So there is a key derivation mechanism happens. You see those components. So when you do the initial authentication, you authenticate, authorize, and finally you come up with these keys, integrity key, encryption key, because whatever you are sending, it has to be encrypted, right? So it is important to make sure if I'm connecting, my data is secure, right? And my signaling is secure. So this is how you get these keys. So now you see the high level picture of how I need to secure, but story doesn't end there. So while 3GPP has taken care of the fundamental security, you see there are additional features 5G has, right? And you have software defined networking, right? That helps to program the routers and switches on the fly. You have open source. We are getting open source has lots of problems. AI/ML, I'll talk about that later. Slicing. So slicing gives you the quality of service, but one slice can attack another slice. It can do the resource starvation, right? If I'm an end user, I'm connected to two slices. One slice is more trusted than another slice, right? But I can be the potential breeze between two slices. Virtualization has a lot of good effect because due to virtualization, I can scale up the network, scale down, right? But virtualization, you just hypervise it. So, I mean, when I was in AT&T, we used to take care of this problem, right? Hypervisor at best attack. Orchestration, that means, what is orchestration? So if I have one AMF or network function, and there was a load went up, so I have to install 10, right? Now, that means I have to instantiate, orchestrate and instantiate 1 to 10. But when I'm orchestrating, maybe it's not going to orchestrate in the right place. Maybe it will put a different. So basically, that's the orchestration attack. Then people have started looking into physical layer security, because there is a MAC layer, which is Wi-Fi, layer 3, which is IPsec VPN. We all use that, TLS. But people thought maybe having physical layer security on the web form is better. Quantum satellite security, predictive. That means before even the attack happens, if I know attack is going to happen, I can stop the attack, right? That's called predictive. That's where AI/ML helps a little bit. Supply chain security, this is also important, right? Because when we get from different vendors around the world, and some vendors do not follow the security practice, it can extract the data from my network, right? So we have to worry about that. Then edge cloud, this is why do we need edge cloud? To support ultra reliable low latency. So for example, now AT&T, they have hundreds of edge cloud around their core. So a lot of processing takes place at the edge, but edge cloud may not be 100% secure, right? So there is a potential vulnerability there. So what I've the key takeaway from the slide is while 3GPP is doing all the fundamentals of securing the network, these are additional components that keep getting added, right? For example, 6G will have more stuff getting added. So we have to think about security for those. Now, I will give some experimental results now to show what is going on. But before that, I'm showing what actually happens when you connect, right? So you saw the actual network. So this is my user endpoint. This is my radio access network. And these are all the components on the back end. So we happily use it, right? But look at how much of hard work people have done to come up with an architecture and, and make sure this actually works, right? So a lot of work, right? And if you look at those documents, 3GPP documents, they're like hundreds of pages. There are lots. Anyway, so what I'm showing here is initially, when I'm connecting registration request, I do all the interaction. These are the protocols I talked about, which is HTTP. And I'm showing the potential points of attacks, like during my registration, right? Denial of service, jamming attack. Control plane means I'm connecting it. HTTP API-based attacks because they are all using HTTP. Data leakage, attacks on the NGAP, these are all protocols. So during the connection, I have a problem. I may not be able to even connect, right? Because somebody else is hijacking my session. So once I connect, then I have to send my data, right? And data goes in a different plane. So GTP is another protocol, GPRS tunneling protocol. Sorry for all these acronyms. But then when I'm sending the data, somebody may hijack my data. Somebody may change those informations, man in the middle attack. Somebody may change the quality of service. So I have to see how do I take care of that, right? So having said that, now how do we come up with a framework to take care of this problem? So this is just one framework I'm showing. So let's look at this. We call it security as a service to provide the resilience. It's like a closed loop automation, right? So these are my endpoints. So they may send attacks on the control plane or data plane. So if these attacks are coming, and this is my 5G core network, and these are, let's say, my control plane function, this is my user plane function. And so I have to have a way to detect the attacks are happening, right? So let's say somebody is trying to send lots of attached requests, right? That means nobody else can connect. Somebody is saying malicious traffic, nobody can send other traffic. So I have to have a way to detect that. Then I have to tell my denial of, DDoS or IPS, and these are the intrusion detection system, intrusion protection system. I say, okay, think about it. There is all in, I mean, I used to, in GNOG, I don't know if you have seen, in AT&T, there was a global network operations center, like IMAX theater, like there are 80 ports, and the analysts are sitting down and looking at what's happening in the network, right? And they see some spike, they go and say, okay, root cause analysis, who did that, right? And they figure out who is attacking it. So this is what happens. So if I see a spike in the traffic, but I don't know who is attacking it, I have to do a little bit of deep packet inspection. That's where IDS comes. Once I find out these are the endpoints who are attacking my network and the location that the IP address and other parameters, then I can stop it, right? This is where the SDN controller does. So the idea is I have to detect first, then I have to apply the firewall rules or whatever to stop the traffic. But at the same time, what is happening? Other people cannot connect, right? So this is called resilience. So what I do, these are the virtual functions, right? AMF is the control plane, this is the user plane. So if I have one AMF, I can instantiate, make it like 10, right? Just for the transient, the perturbation happening, right? So then once the attacks are subsided, because I mitigate the attacks, I bring it down. So one AMF scales up to 10 during the attack. One UPF scales up to maybe whatever, 5. Then, so my quality of service is still maintained. That's called resilience, right? And so this is the whole idea. It's called closed loop automation. So what I'll do, I'll show you some experimental results we did, so you know how actually it's done. So attacks in a control plane, let's focus on that, and then the user plane. So this is how I'm taking a subset of the thing. So you have my control plane. I'm sending my attack using these protocols, and this will percolate to others because it's a cascading effect. And on the user plane, I'm sending lots. So this endpoint gets infected. It's a malware. And then it starts sending lots of malicious attack, right? So my UPF, which is user plane function, is under attack. So this is what is happening, right? Attacker is attacking those. So I'll give you some results here. So what you see on the left-hand side, this is control plane, right? So normal attach is happening. All of a sudden, there's a spike. So when the spike happens, that means if there is a spike, other people cannot connect because the bandwidth is limited, the server is under attack. So I have to mitigate that, right? In this case, I have to do this analytics. I see the spike in NGAP packets. Then I do the drill down. Again, this is all happening automatically. Then I see, you cannot read this properly, but it says the origin of the attackers, right? The IP address, IMEI, MC, etc. And then I apply my mitigation part, right? So I reduce it. So during this time, I also, scale up the other components. So this is the control plane denial of service. Same thing happened in the user plane. So user plane you will see is bit per bit rate, right? Megabit, gigabit. So my traffic, normal traffic is about 150 or whatever, 160 megabit per second. And one of the end user got infected. Then it may be deliberate, maybe not deliberate, right? The user starts sending voluminous traffic and become 1 gigabit per second. So what will happen then? Your UPF is overwhelmed, your bandwidth is limited, other people cannot use the network. So in that case, we have the intrusion detection system. You see the spike, then you find out who is attacking it, right? We do the drill down, then we reduce it. So this is another application of this framework that I showed, how I took care of this problem, and I don't have a slide to scale up, scale down, but I usually do that for my class, but we don't have enough time, right? So this is another example of voice over IP. So this is where same concept. I just talk about a little bit here. So what happened is my normal operation, this is a mission critical user. SIP is a session initiation protocol where I make a call. And then a rogue user comes and sends malicious traffic. It saturates the user plane. Then my RTP is real-time transport protocol that we all use. The mean opinion score goes down. My packet loss goes up, right? So that means if I have a mission critical user, I cannot even place a call, or I cannot even understand what the other person is telling, right? Because affecting my the voice quality. So then we used, Nixon is a company, intrusion detection system. We detected that and we stopped the attack, right? So this is another example of that. And these are some results for that, right? It's important to know the results. So let me spend a minute or two on this. So you saw the experimental setup. So what you see here, the bit rate, Morse code, loss count, right? So when the attack took place, my Morse code will go down. So I have a dip in the Morse code, right? Then my loss count also went up, right? Because the attack is taking place. So that means it's called degradation of service, right? Remember there are 5 things. So this is applied to degradation of service. So my service is not degraded. Then I start my mitigation process, right? I need to know who is attacking him now. So I start my mitigation process. I see the alert, who is doing it. Then I start putting my enforcement policy and everything. Then you see the thing went away, right? Your loss count went down, the Morse code went up, right? So this is just another example of a specific application, which is user application. I'll show you 2 video here just to make it a little interesting because you have been just listening to me. So this is an IEEE 5G 6G testbed we have done. And we wanted to, it is available anybody in the world, like even UMBC folks, anybody. And JHU, I have access to that too. So what I'm showing here is, I'll play the video. What I just said, right? You'll see, sorry. Excuse me. No, not. I think something happened to any other. Forget it. So basically it was showing how I instantiate. No, link. Okay, let's see. This is the dynamic quality of service. Anyway, that's fine. I'll show that later. This is another example of what is happening. So you're streaming a video through the network. Congestion happened, right? Then how do we react to improve the video quality, right? So whole idea is, talking about when there is this rocket is going up. They should be coming back today, right? So then somebody created a congestion. In this case, we are actually doing it ourselves. And you see the Morse code went down, packet loss went up, the video quality suffers. So how do I take action, right? So I use like Camera API, and you'll say I mark the packets. So basically, some of the packets I put them in a priority queue called dips of core point, right? And then you'll see the remarkable difference of so this is before congestion, priority, and during congestion. During congestion, things are still bad. I'm just comparing, right? So this is one way to how to take care of this, right? And the other video I think embedded, that's fine. You got an idea about the previous one. This is another way to apply this closed loop automation, and you make sure that you give the right. Okay, so now I've got about 15 minutes, right? So I'll very quickly go through systematically how do you apply. Okay, this is a paper we wrote 2020, but so now you see the 5G has 3 components: radio access, you have core, you have application. Now, if I'm an attacker, right, I want to do bad things. These are the things, kind of requirements, loss of availability, confidentiality, integrity, loss of control, malicious insider, theft of service. So hacker will try to affect all of these, right? Then how do I do it? If I want to make the network unavailable, I just plot the interface, right? Send denial of service attack, just I showed, or cross a network element, right? So I can do that. This is the RAN. There's the RAN piece on the RAN side, which is on the over the radio, via RF jamming or G node B. You saw those examples, right? Now for each of those, I have potential mitigation technique. So this is how you have to go. We call it threat taxonomy for each of those, right? A loss of confidentiality. That means you're eavesdropping, man in the middle attack, changing the parameters, loss of control. So, and this is on the RAN side. Similarly, on the core side, same thing can happen, right? So RAN is over the radio, and core have similar problems, right? So first two columns are remaining same. The key takeaway is every network has different protocols and even the part of the network, right? So in this case, I have a control plane and user plane. I'm not reading everything here, but those protocols can be affected, right? And those information can be affected in the code. And then I come up with mitigation technique, just like I showed one, right? Then the last piece is the voice over NR, they call it IMS, IP multimedia subsystem. In 4G, they used to call VoLTE. So in this case, I'm using a protocol like SIP and RTP. So sometimes we might have seen that, like spam over internet telephony denial of service attack, right? So these are the kind of attacks happen. Somebody can just keep on calling and calling, right? During robocalls, they call it, right? And this happens during election time. And sometimes when people steal the parameters, I'll see as if my mom is calling, but somebody else is calling, right? So those kind of things happen. So these are the types of attacks, and for that also I have potential mitigation technique. Okay. So this is how you progress in a very methodical way. So I'll quickly go through some of those things I showed in the circle. So open source, I don't know if you are aware with open source means everything is open. You don't have to depend on any vendor, right? You all use that. So open source, again, those are the 5G, 6G related open source. On this orchestration, you can get your own 5G code. So it has its own advantages and disadvantages also. So we have to look at the security associated with that. I talked about supply chain. And now that you know the network, we have to, so these are some vendors who are providing around the world, right? So you have user equipment, radio access, then you have the core network you saw, and there are chips also, right? So now all these things are coming from different parts of the world, different vendors. So they have a responsibility to make sure those are secure, right? Otherwise, our data can be exposed when you are using it. And there are people have come up with different criteria. What is happening? Include computer sound. Looks like you are sharing video. Okay, I see. What's this? Okay. Anyway, so these are the best current practice. Then I'll give a few more examples. We talked about SDN. So let's see what is the problem with SDN now, right? So this is a little a smaller version of the picture I showed. So attacks are happening. You see something happen, then SDN controller goes and dynamically put the firewall rules, right? So this is the advantages. I call it opportunity. So what is the problem now? See this specific. When I was in AT&T, we did that. So the Open Daylight is a open source. We used it in the lab. Then that it has a bug, right? So external XML entity attack, the hacker goes and changes the configuration. Now there's an oversight, but there are other things could happen too. The one on the bottom you see, we did it in the lab. Somebody attacks on the southbound side. So there's a northbound, there's a southbound, right? And the whole SDN controller was under attack, and we could not do anything, right? So think about in AT&T's network, if you have an SDN controller and people are using it, all of a sudden somebody comes and attacks, then the calls cannot be even routed. So what we did, this is another way to look at the attacks. Then I talked about risk, right? And there are different classification of the risk. Then I talked about types of attack, right? Denial of service, degradation, etc. So I'm putting all of this together here and how it's affecting, in this case, NSEP is our mission critical user, first responders. So this is a project we did for Department of Homeland Security. And so what I'm showing here is the potential opportunities. The SDN controller provides the resilience, right? It enhances the programmability, dynamic service chaining, security control mechanism. So these are the good stuff. Now, what are the potential attacks? So denial of service through southbound, REST API, northbound API, man-in-the-middle attack, protocol fudging attack, right? These are the, I just listed few of those. Now, how does it affect the NSEP users, right? In this case, let's say wrong configuration of SDN controller will route the mission critical users traffic to a wrong destination, right? That's a bad thing. Inability to program the controller will affect the proper routing. Change in API parameters will adversely affect the mission critical user and user data, right? So these are the bad thing could happen if somebody attacks any of these attacks. Then, and what kind of attacks are those? Is it service degradation? Is data manipulation? Then the risk severity, right? If something is green, that means I am good. My network is good. I don't have to do anything. If something is red, that means there is a vulnerability, right? There is a risk factor is high. Then I have to apply some mitigation technique to reduce the risk factor, right? So those are the potential mitigation technique. So what we did, and I'm not going to go over each slide, but this is the SDN controller, same thing on the slicing. I just two examples. So slice, as I said before, you create a slice for each type of user, right? The ambulance, the fire, and police, and each slice have their own quality of service requirement, right? Now, one slice, because they're using the same physical resource, the same thing, right? The memory, CPU on the same box. So one slice can attack another slice. One user endpoint is connected to two slices, right? So these are the kind of things. So we did the similar thing here too. So slicing enables service differentiation. These are the opportunities, right? Isolates highly sensitive context, reduces the security overhead, right? But then potential attacks here. This is again, I'm not take maybe one or two example. Side channel attacks across slices extract information about the cryptographic keys. Denial of service to other slices like resource exhaustion. Sealing between slices when one endpoint is connected to different slices. And then we did the risk severity and potential mitigation, right? I'm trying to look at the slide and I'll skip this open RAN security, which is when radio access network is cloudified, right? Then mobile edge, this is also important, talking about low latency application. What you're doing, you are putting lots of edge cloud around the core. That's the core, right? Now, so security context, these edge clouds are not that secure. So what happens, the whole idea is if a mission critical user and low latency requirement, I process them in the edge cloud, not in the core, right? But think about it, the security context is not secure, then it'll be under attack, right? So that's why, we did the same thing here too. Things like gas poisoning attack, spoofing attack, eavesdropping, and then how it's going to affect the users, risk severity and mitigation, right? So this is just to give you an idea. Then other thing I didn't talk about, we are using new protocols, HTTP, right? You all use it today. If 70% of the protocols in 5G core are HTTP, HTTP itself has problems. And this is from FCC, CIDRIC. So they came up with, hey, make sure if you're using HTTP, these are the existing security risks. How do you make sure your network is secure, right? And so that is on the control plane. The same plane on the user plane, right? I showed the example of GTP, which is GPRS tunneling protocol. So because I'm sending through GTP, they also have different kinds of threat. It's dropping fraud, malicious GTP messages. So if I do a analysis of that, how do I make sure my GTP traffic is secure, right? What else? API. Now, application programming interface is also important, as you saw. So I have to make sure when I'm trying to orchestrate or trying to change the SDN controller parameters, these are the kinds of attacks happen: injection attacks, broken authentication, exposure of sensitive data, and how it affects the users, what the risk, security, and mitigation technique, right? So what I was showing here is, okay, sorry, ran out of time. So now I give you an idea about the standard security stuff that happens. Now let's see how AI/ML can help it, right? I ran a little late, folks. So AI/ML is used to enhance the 5G operation. How? It enhances the user experience, quality of service, personalized services, energy efficiency, traffic management, anomaly detection. We'll focus on that a little bit. Operation management, service-oriented network, predictive maintenance, right? So again, AI/ML has a lot of avenues, but let's focus on the security. So now that you understand the security aspects of 5G, so it is all signature based, right? You saw the malware. I think there was somebody who was doing malware, he left. So if you detect the malware, but sometimes you do not have like a zero trust, right? Or zero-day attacks. So you may not have that. So signature-based detection, that is a one of the limitation. Rule-based systems. So complexity of dynamism of 5G networks make it difficult. Manual threat analysis, human intervention, perimeter-based security, access control policies are fixed. So these are some limitation of the conventional security methods. So how do I apply AI/ML to take care of the complexity of 5G? So some of the challenges, as you saw, massive data volume, high dimensional data, network complexity, different types of device, dynamic threat landscape. You saw different types of threats, real-time threat detection, scalability, zero-day vulnerabilities, right? So for each of those, AI/ML can be used to effectively detect and monitor. So for example, the first one, effectively process, analyze the vast data to identify potential security risks. High dimensional data, capable of learning from high dimensional data, identify complex patterns, etc., right? Handle complexity by learning and adapting to the intricate patterns. So this is where the predictive security comes, right? If there is an attack happening, how quickly I know, okay, this, based on this pattern, this attack had happened. Now I'm going to prevent the attack altogether, not reactive, predictive. This is what, learn the unique behavior patterns to detect anomalies. Adapt to changing threat patterns, process data, identify. So AI/ML has the ability to do that. So if I try to make a summary of that, enhance IDS, the intelligent detection system, incident response, task automation, threat prediction, risk scoring, prioritization, vulnerability assessment, predator learning, malware detection. So these are the different areas where AI/ML can be used to help. Again, these are the definitions of all of those. I can share the slides if you can share with us. Yeah. I'm not going to talk about all those, we're running out of time, but here then once you come up with a AI/ML framework, right? So you saw the 5G infrastructure. What 6G is doing, they're trying to use AI/ML agents and put this across the network. So you need to have on the 5G infrastructure some security data collection module, data preparation module, and then machine learning based security modeling, and then you basically apply that, right? So that means you probably need agents in all those network elements I showed. You need some kind of a language or protocol so that agents can talk to each other, right? Because it is not only one system. You have to look at everything going on in the network. So once you have that, you apply it. And again, this talks about all the description. And basically it works, right? And I think there is it is from, there is a reference there. So other consideration, AI 5G security complexity, adversarial ML, explainable AI. So I'll talk about adversarial ML a little bit. So adversarial ML means now we can use AI/ML to our benefit, but AI/ML itself can be compromised, right? So poisoning, supply chain attack, exploitation of deployment environment, evasion, model inversion, model extraction. So these are the types of attack, and these are the description for those. So just like we came up with the defense mechanism, what if our AI ML framework or thing is attacked? We have to have defense mechanism for each of those, right? So this is where I'm showing if I have a poisoning attack, what do I do to defend it? If a supply chain attack, what do I do to defend that? If evasion happened, model inversion. So this is how you go in a systematic way to take care of that. So again, AIML people are still checking it, and 6G probably will deploy more than 5G. So it's applicable to securing 5G system. The scalability, diversity, complexity, nature of 5G, it can help. Effectiveness of AML is security unclear because people are still experimenting that, right? Just like I showed the experimentation, we haven't even tried those kind of experimentation here. So due to lack of industry benchmark, case studies, best practice, is difficult to find out the effectiveness, but it's going to be there, right? This is an interesting study now going on. Can I give 5 more minutes? I'll finish up.
Yeah,
Is that okay?
sure.
So,
We can go.
Yes.
We can go
Oh.
as far as possible because I think.
yeah, I don't want to keep you for a long time because I just want to finish with this test bed thing. This is important, right? So what is happening? NSF, they realized that we need to have experimentation, not only theory. So NSF had come up with something called Platform for Advanced Wireless Research, Powder. This is in Salt Lake City, Cosmos in New York City, ARA, which is in Iowa. This is North Carolina, and Coliseum that used to be at APL, now it is Northeastern. And so now that you saw, if you want to build something, and I'll give you some use case, you try it in your university or anywhere, then you go to these places and try to do the scalability, right? For example, I'm talking about millimeter wave. You go to Manhattan and try to see how this works. Or you want to do massive MIMO type thing, you go to some campus in Salt Lake, I've been to those 2 places, or any robotic stuff, drone stuff, you go to North Carolina, right? So this is a good way to collaborate, right? But before that, okay, I think this is a test bed, the IEEE 5G60 test bed. I showed one example of that. And this is open to academics right now. If anybody interested, please let me know. So what I'll show you now, remember when I started with, you come up with some technology, then you'll see how it's going to help. So Department of Homeland Security came to us. Unfortunately, these things happen nowadays in the United States. And they came to us because they have to make sure there's an active shooter scenario happening. They're depending heavily on this network, right? If the traffic don't flow properly, traffic drops, they cannot call people, there's a problem. So they give us a list of pain points. High latency, like 10 seconds streaming video, which is not effective, interruption during handoff, high bandwidth application they could not send, information overload, like 10 different pain points they get, right? Now, we want to know, can 5G solve it, right? That is the whole idea why we're doing 5G, right? Because we want to solve the problems. So we did a gap analysis before we even do the experiment. So it's a high latency, okay, fine. We have edge cloud that can take care of it, right? You have, I'm just showing 3 examples. As incident unfolds, surge in the number of calls, data traffic, right? So lots of people come, right? Thousands of people or parents, they all come, and what's going on. So we have the software-defined networking, network function virtualization that can dynamically scale up, scale down when that happens. Information overload at the dispatch center, we can use network slicing for that, right? So this is where you're trying to look at the pain points and trying to see what solution, right? I think in the industry, like when we work with DARPA or DOD or DHS, they come up with this and what is the transition, right? So first you do a gap analysis paper study. Then what you do, we actually do a prototype. And then you go to this NSF bigger test bed to try it out. So this is what we did. I was personally involved here. So this is the closed loop of automation and active shooter scenario, the example I said. So we had a 5G core. We created an active shooter scenario. We have a data analytics. We have an orchestration module. and you see those network control function and user plane function, right? So what happened, initially we created only one call, right? Then we simulated thousands of calls, right? So by doing that, we saw there is a strain on the network components. We see the data analytics, packets are dropping. Then we did, I think I talked about it, right? You can see we scale up the network from 1 AMF to multiple AMF, right? So we, in effect, this is called performance overload. This is not denial of service attack. It's a real thing, right? So people have started calling. So that problem went away, right? And then they went and they said, okay, 5G has the ability to do it, and they go and they try to deploy it. Next one is, it was taking a lot of time, 10-second delay for video distribution from the incident scene. That's not acceptable, right? So now we have edge cloud. So what do? We see the it's taking 10-second delay. These are mission critical application. So use the data analytics on the fly. We instantiated the local UPF. These are the user plane function. So those applications, instead of getting processed here, they got processed here, right? So we reduced the 10-second delay to 5 millisecond delay, right? So this is how you solve a problem. The third example was slicing, right? And then there are some security stuff we had to think about. Again, I talked about those, so we had to worry about those things. So also automation instances as cloud service to support ultra low latency, right? This has happened on the fly. The third one was the slicing, which I talked about here. How we created multiple slices, and we gave the slice to the mission critical user, right? And this can happen also instantaneously. So I just placed a few slides before I close. This is close to my heart, and as we started this Future Networks technical community in 2017, one of the founding co-chair. Right now, it transitioned, became an initiative. Technical community. So ComSoc, I'm a member of that. And there are multiple societies. IEEE has about 46 or 47 societies. So we do a lot of work. We do a roadmap, connecting the unconnected. I talk about it. Fast responder tactical networks. We have been doing it at APL for the last 7-8 years. The Future Network World Forum. This is the roadmap. So if some of you are interested to contribute, it's open to anybody, right? So this is, it provides publication standards, education, webinars, conferences, all of those. And it's a multi-society because we think it is not only communication, right? It has to be other. So what we're doing here, you saw the initial, the 5G and 6G stuff, right? Now, this is the circle I was showing, the 6G. So all the work we are doing, these are different groups. So you have about 15 different working groups: edge, security, massive MIMO, energy efficiency, optics, satellite, security, privacy, standardizations, testbed. So what people do around the world, they come up with how things are going to look like 5 years, 10 years from now. So this is very researchy, right? And then we are trying to map how it's going to help. See the IMT 2030, right? That's the 6G. So because it has to be relevant also. You cannot, we can always think about research 50 years from now, but we have to also be a short term, right? Short term, mid term, long term. So some of these things we are doing are that directly related to 6G. This is also very close to my heart, which is connecting the unconnected. So 50% of the world population, they are underconnected or not connected. So we came up with this initiative. We started something called Challenge and a Summit. So people can submit ideas if they have a prototype, and we give them money also. So technical application, business model, community enablement, these are 3 areas. So we have been doing that since 2021. And what good thing has happened out of it, a lot of venture capitalists now came to us. They said, like Lemonson Foundation, for example, they said, okay, these guys are very interesting projects. Can we try to implement that on the ground? So they gave us money. They said, okay, create some mentors, talk to VCs. And so this is how some of the technology we are developing, how this can be used and help the community, right? So this is, for example, we just concluded last year, 2025, 245 submission, 52 countries. And then you went through several screening process. So 14 submissions selected for monetary awards out of 245, right? And then we have a mentors, mentees. So for example, Vin Cerf, he is one of our industry advisory board, and this comes from all over the world, right? So there are some concept means you just have an idea. Proof of concept means you have something working, right? And some of the concept can go to proof of concept. So this is again humanitarian work we are doing, and these are some example of it's the radio bolo, which is like having radio station in the villages. Actually, this got an award also called Community Radio Bolo. I just give you some example of strengthening the local communities, sustainable ecosystem. This is another one. Bamboo towers for low cost affordable internet. Like instead of people when they have lots of bamboos, they can put Wi-Fi access point. They don't need any. You don't have to put a new pole or something to give the access, right? So take advantage of the natural resources. Then this is open source portable offline fast wireless mesh network. Again, this they're using open source. It's also one of the. This is from they already have started deployed in South Africa, Canada, and other parts of Europe. Just wanted to give, this is another one, affordable internet access devices through e-waste recycling. So there are many, sometimes when you listen to these people and the kids and students, they get so much benefit. It really helps. So we have a CTU newsletter. So this is, I'm showing how use the e-waste recycling in Uganda. And so they also won the award. I'm just showing 4 things. We recently did something in near Bangalore in India last November. So IEEE said, okay, you have all this technology, can it be applied to villages? You know, we just took an example of Bangalore because we had our Future Network World Forum. So we went to a village Gram Panchayat, they call it, like 8 or 9 different villages. And we brought these people who got the award winners, right? And we just, and Move Truck is another one. So they see the kids. And so now we are trying to bring, this is Sudhir Dikit, who is my co-chair. And we showed, and the lady over there is CR Bolo, PI for that, right? So just wanted to show some of the humanitarian work. I think I just have 2 slides. So now I wanted to give you an idea about what is 5G, why do you need new technology. But when you develop a technology, there are also a lot of pain points, right? It doesn't happen overnight. So in terms of adoption, in this case, we're talking about 5G, and same thing will apply to 6G too. Densification of cells, spectrum sharing, security, heterogeneous mobility. I think I talked about some of those. There are radio frequency issues, backhaul, midhaul, coexistence with satellite. I briefly talked about that. On the core side, you see the transition coexistence, right? With whole network is not completely 5G. Part is 5G, part is 4G. Coexistence with other networks like Wi-Fi. Then SDN, NMP deployment, microservice, which is the service-oriented approach. Open source, we talked about it. There was a lot of hue and cry about cultural barriers like health, safety, you know, it keeps coming now and then. Some point, United States State Department, they sent me to Europe when the security thing was coming up. They said, okay, you were doing this IEEE thing, go and talk to them about security issues. A lot of people ask me that question, right? There is no, I mean, people are still talking about it. Then some people make a claim, then they go back. But it still should be careful about. I talked about digital divide, a legacy network, how 5G to 4G, you know, back and forth. That is an important thing. That if we fall back to 4G, well, my network will be affected. Vendor interoperability, supply chain, roaming among operators, spectrum interoperability. These are like policy related stuff. And spectrum, this is a little interesting and researchy too, dynamic spectrum sharing, you know, if you have scarcity of spectrum. So finally, what I started with, I wanted to close it out. So we need a new network to make it adaptive, resilient, and flexible, because we need to support new application. This is the very first slide. So, and I showed how we took an example of 5G. So 5G network gives rise to additional security pillars that are often inbuilt and have opportunity challenges like resilience, automation. These are some of the opportunities. The challenges like side channel attacks, I gave you some example, right? If you focus on security. So if you have to attack that, you need a systematic approach to threat analysis. You need a threat taxonomy. You need the security controls, implement the best current practice. These are important, right? I went over some of those. Then with AI ML coming up, let's see how AI ML can help, but at the same time, AI ML needs to be secured and should not be compromised. Then finally, I talked about collaboration among operators, vendor regulators, which is important because in an ecosystem, you cannot just keep the standard or do the research and leave it, right? It has to, some of those have to be at least used. So that means you need, if you have a research idea, go to standards, try to see if that helps, build a test bed, try to do proof of concept actually works, and proof of concept, and then go to bigger test bed, right? So this is my last slide. So, and I know that this is being recorded. I'll send all the slides
Yes.
so you can share with folks.
Yeah, we have a website and then we can
Okay, that's great.
share everything
Yeah,
with it.
And I look forward to more collaboration. I know you're a faculty here and PhD students. And the Baltimore chapter, let's do some program together, right? Because I know I'm talking to Professor Joshi when he gave a talk. He said, let's do some events here because we have been doing mostly at APL and maybe we can do something at UMBC. Thank you folks for on the breeze if you're still listening to me, and thank you for inviting